Hello to everyone. Thank you for organizers. It's a great pleasure. It's a great pleasure to share this session. This is the first one, and the most friendly and interesting fuzzy conference. So the first, we will have, unfortunately, 3 talks. We are not going to have the fourth. We have like 20 minutes for each, and we have time for the questions a little bit more than usual, because we do not have the fourth author. And so we start with the first presentation of Dvorek, Antonin, and Stepnichka Martin on properties of Mandani Asian fuzzy rules and open problem posed. Please, Martin.
Thank you very much, Olga. Thank you very much. Good morning once again. And thank you for the kind words about friendly atmosphere of this conference, but we should definitely emphasize that Olga is the organizer of next USFAT conference in Riga in Latvia 2025, and there will be at least as friendly atmosphere as this one. So thank you for your words, but we are looking forward to meet your hospitality in Riga, so please keep this in mind. And now let's go to the scientific part of this session. I will talk about Mandani Aselian fuzzy rules, which are rules which I actually didn't like for a long time of my research. But then we were thinking that they maybe have some reasons of existence, and why I will try to explain why we are interested in researching this topic. So they didn't. It's good to have technicians close to you. So everybody knows what fuzzy rules are, just such sentences, conditional sentences, and they are central notions of fuzzy modeling. And mostly we model them in the conjunctive, or if you want, Mamdani-Aselian model, which I will denote with this check sign. And it's clearly this disjunction of conjunctions of antecedents and consequence. I mean, I'm talking about fuzzy sets. Implicative model is a conjunction of implications. And the involved operations are from an underlying algebraic structure, usually some residuated lattice. The block structure of fuzzy inference system is as follows. You have the fuzzy rule base, which you can see as pairs of antecedents and consequence. You model the fuzzy rule base by some fuzzy relation. Then you have input, which is a fuzzy set on X, and some inference engine together with rules will give you an output, which is a fuzzy set on the output space Y. Normally, these inference engines or inference mechanisms are either the substar or compositional rule of inference, if you want. Composition, which is given as follows. Simply you have the input. You put it together with this circle signed with the fuzzy relation that models the fuzzy rule base, and you will calculate it with the help of this formula. An alternative way is to use the Butler-Kohu subproduct, where you denote it with this triangle, and you will get it by this formula. And it's good to keep the preferable pairs that whenever you deal with the compositional rule of inference, you deal with the implicative rules. While if you deal with Butler-Kohu subproduct, you deal with the Mamdani-Aselian rules. You can, of course, still mix them and deal, for example, with the compositional rule of inference and Mamdani and vice versa. But there are very good works, scientific works, that are telling you that this is definitely not the preferable choice you should take. And if you take it, then it should be under specific, very strict conditions. What are the desirable properties of rules and fuzzy inference systems? Well, usually the most desirable property that is investigated by many authors is the consistency, which says actually there should be 2 rules with the same or very similar antecedents and 2 different or far located consequences. For example, if the obstacle is in front, direction is left, and if obstacle is in front, direction is to the right. Often means that if the obstacle is in front, then you should split the car into 2 pieces, which is physically either impossible or very harming the car. So this is definitely not what we would like to encode in fuzzy rules, that we have the left and right choice at the same time. This is usually investigated via fuzzy relational equations and their systems. If the input is one of the antecedents, then the desirable output, the expected, the one we want, is the related consequent BI. This leads directly to the solvability of systems of fuzzy relational equations. So we have 2 systems depending on which inference we use, or which engine, which composition, which product, if you want. And we say that this system is solvable. It's a system because we have n of them, as n rules, and we have n such equations. If and only if the implicative model is the solution for the first one, or if the Mamdani-Aselian model is the solution for the second one. That's why we have these preferable pairs, which I have mentioned. And then we say that the model, which is the solution, is a safe model of fuzzy rules from the interpolativity point of view or from the preservation of modus ponens point of view. So it's nice from the interpolation geometric, say, interpretability point of view, or from the logical motivation, which we may also have, which is the preservation of modus ponens. And there is also one nice result, which I would like to mention, that you can ensure the solvability in advance if you impose finitary condition on the antecedents. Finitary conditions are encoded as follows. You can imagine them very, very easily. It's like the weakest disjointness you can imagine. It says that for any such a fuzzy set on the antecedents, you at least find one node like this that belongs fully to one of the fuzzy sets, and it doesn't belong to any other. So even though these two fuzzy sets, A3 and A4, are overlapping in cores partly, it's still fine. You don't need Ross-Puini condition. This is much weaker, and still this ensures your solvability. So this is nice. If you have it, you have solvability because it's a sort of disjointness. If you have disjointness, you cannot have two antecedents too close to each other, say, because of disjointness, and still two consequences that would be too far because you don't care about consequence anymore. Good. That was about solvability, consistency, and so on. But the idea actually is behind that we cannot go left and right at the same moment. But recall, functionality is defined as that there are going to be two different outputs for a single input. That's functionality from mathematical analysis. Lipschitz continuity is that the closeness of outputs is determined by the closeness of inputs. And there is a nice work of Irina and Stefan Lemke that actually is on the topic, showing that actually these correct models or the solvability or solutions to the systems are actually somehow equivalent to a sort of Lipschitz-like continuity. So wait a moment. At the beginning, there was a sort of logical correctness. We were talking about modus ponens. But it led to non-conflicting rules, and consequently, it turned to some sort of functionality or continuity property of the dependency that is described by the rules. So actually, it says we will have logical correctness if the rules describe functionality or if they describe sort of continuous dependence. And do we always have to consider two rules with similar antecedents and far located consequences really to be inconsistent? Isn't it reasonable only in the case of implicative rules? A toy example, avoiding a puddle. You have a kid, and the kid is supposed to avoid a puddle. If you give the kid these instructions, if the puddle is in front, then direction is left, and at the same moment, there's conjunction. If the puddle is in front, then direction is to the right, then this is clear inconsistency. You cannot do it, otherwise you would have to split the kit into two pieces. This is really broad. But if you control the kit with Mamdani-Aselian rules, the rules look like this. Puddle is in front and the direction is left, or puddle is in front and the direction is right. And there is no problem with inconsistency at all, because they are aggregated disjunctively in the Mamdani-Aselian model. So I don't think we need it. Thus, we don't need solvability. Thus, we don't need functionality. We don't need continuity and so on. The only problem comes when you apply center of gravity, because you have left and right, you make center of gravity, which means go into the middle and you face the obstacle. In this case, you jump into the puddle. That's what happens. So the problem is that we just have in mind always the fuzzy control case where you need the function. But if you speak about other problems, not control, but you talk about, for example, some decision-making situations where you have several alternatives and they can be disjoint, and you forget about using any defuzzification, it's totally fine. So what should be the requested behavior? If you have rules that go to the left and go to the right, you just want to get something which is not more or not much more than the union, and then the alternative to go in front is excluded, and the kid will not jump into the puddle. So something like this on the output is no contradiction at all. Although it's harming the solvability of fuzzy relational equations, it's not contradiction, and we shouldn't misinterpret these things as long as we deal with Mamdani-Aselian models. So let's go back to the fuzzy case and to the solutions we may get or some results. If we have some rules, and let two antecedents are equal to each other, then what we get immediately is this inclusion. So this is like an upper bound, upper estimation of the output of the inference. I will be dealing with only bundler cohort and Mamdani because I said I'm investigating Mamdani, and I said that bundler cohort subproduct is like preferable inference to Mamdani. Yeah. Conjunctive connection between antecedent and consequence and disjunctive aggregation of rules. Yeah. No assumptions, no normality, no finitory. We just have this automatically. Of course, we know that this is like bigger. So I said upper bound, this is lower estimation, but we don't be much bigger because that would allow us to jump into the puddle. This is left, this is right, and we don't want to be much higher than this. If we add finitary condition for all the rules, but not the jth rules, and the jth rules is actually having the antecedent equal to the ith rule, then we will get equality, which is nice. This is exactly the choice of the kid. Left, right, nothing more. What it means, what the result actually tells us. Give me a system with antecedents meeting the finitary condition. Over there. It is solvable. So it describes functionality, it describes continuous dependence, and so on. And I'm adding one more seemingly conflicting rule that enables you to have one more alternative, not only going to the left, but also going to the right. I will infer the union of the two alternatives and nothing more. And I'm happy because then the kid doesn't go to the puddle. So, okay, but let's go on with the Mamdani ascendant systems. And we actually now stopped asking whether they are somehow conflicting or not, but we try to investigate how they behave. We want to understand them, what they describe and how they behave. So again, we have all antecedents meeting the finitary condition, and we add one more jth rule. What we get is that if these rules meet the finitary condition, so just the jth rules is the edit one, otherwise they meet the finitary condition, we can get this upper estimation. So the output is the ith rule, that's the ith consequence. So with the ith antecedent is the input, ith consequent is the output. Disjunction or join, if you want algebraically, plus this, where x star is an arbitrary point of normality of AI. If it is arbitrary, we can ask for the smallest one because we want to get the best approximation, the best estimation. So we ask for the smallest one, and we will get this estimation. So we have somehow the upper bound of the inference. It tells us what will be the possible biggest fuzzy set on the output of the inference system. Of course, we also want to know what is the lowest or lower approximation, lower estimation. It is just this consequent, which is very simple. So if you put it together, we get this. So we have the inference, and we know that it's somehow bounded by these two expressions together, which tell us how the inference output will look like. Okay, some example. Here you can see three rules, three antecedents, three consequents. A2 is the input, and this is the inference which we get. And this is the upper estimation which we made. And as you can see, it's slightly higher than this one, but not that much. So it gives us very nice impression how the estimation is precise, how it works. You can imagine this is left, this is right. Here would be the puddle. The estimation makes the right a little bit bigger, but still it somehow restricts our choice to go into the puddle because it's still quite low in the middle. We are fine with this estimation. It's quite good. It's not because we always could expect that the estimation will be that big. Then it tells us nothing. We want to have upper estimation, but as small as possible. Good. Let's play the game with indexes. This was a set of all indexes of all rules. Let M denotes the set of indexes of not fired rules. So we would have this Mamdani-Asilian model of just those non-fired rules. Let L be just the indexes, the set of indexes of the fired rules. Then very easily we get that this inference gives you an empty set, basically on the output, well, or empty information to be precise. And consequently, what we get is that the inference equals only to the inference of the fired rules. So if we have the input, and the input equals to one of the antecedents, and we denote by Li the set of indexes L of the fired rules without this single index, we get this. So we get lower estimation of the inference, and it's given by this formula. It's the BI union and the inference only with the Fires rules without this ICE rule. Very, very simple, very straightforward. So if we have it, and we can also prove the upper estimation, which looks like this, it gives us together the final result, which shows that the inference output is bounded from both sides by these two expressions. And we have quite good estimation how Mamdani-Aslian rules work, and we don't care about solvability. We just want to know how they work. But where is the open problem? Once again, let me recall this result and show some example. Here we have 4 antecedents and 4 consequences. This is the inference if AI is the input. This is what we get. This is, as you can see, the lower bound. And this is just a different way how we write it. This is the upper estimation. If I deleted this, it would be the same. Here, they are totally equal. Then we made another example, and still, and we always got this. We always got this. So we started to have the feeling that there is an equality here, that this upper estimation is always adding something, and we could make it smaller to be as small as this lower estimation, then we would get full equality. But we never succeeded in proving this. Maybe we are just blindly doing still the same mistake. You know, when you just close your eyes and you do it like 100 times, then you still fall into the same trap. So we started to do it the other way. We started to prove contradictions. We started to find like counter examples. We wanted to prove that there is no equality of this, and we get something different, but we never managed to find a counter example. But we still cannot find a proof that would say there is an equality. So the conjecture is that there is an equality, not an inclusion. And the open problem for us is whether there is and under which conditions. And that's actually the end of my talk. If there is anyone who is willing to join us to find this equality or conditions of the equality, that person is welcome to join us. Otherwise, we will have to publish a paper that says we don't have the result, we have just half of the result, and anyone is welcome to join this, for us at least, exciting topic on investigating how Mamdani-Aslian rules work without being bothered what is the solvability of conditions and what is the consistency. But just help us to get the answer on this open problem. Thank you very much for your attention.
Thank you, Martin, for this interesting talk on open problems. Open problems usually attract the students, and I'm sure that they will join you. So some questions, comments, or solutions for the...
This microphone, because we have online. Where did it go?
Okay, maybe childish comment. These compositions, conjunction and intersection, it provides closure or interior operators. Maybe the answer is hidden somewhere in the properties of such operators.
Yep. You're right. It's a good point, but we didn't find a way how to technically employ it into the proofs. But you are definitely right.
Thank you.
Yes, Irina, please. It's
That I should, yeah. You know, just so some flexible association, yeah, because I cannot provide, of course, the solution, but it seems to me also, I agree with the previous comment, yeah, that try to look because so this system is monotonous, yeah. So this means that, yeah, if try to look to the antecedent part, yeah, in the point that if you so how much you can increase your AIs, yeah, in order to have the same BIs, yeah, and keep this restriction. And it seems to me that this can be a way, at least a way, how to find a solution.
Okay, thank you.
Thank you. Some more questions, comments?
Maybe this is not the solution, but I wonder why you are using the same antecedent and 2 different consequences in 2 different rules. Why we are not consider like approximation of relations instead of functions. There is some possibility to do it, or for example, vectors, because we also consider functions that output of these functions are vectors, not just single.
Okay. The idea behind why we started to actually set up this problem like this is that this is what you have in the puddle problem, or if you have like e-state agency and you are searching for a nice place for your holidays, you want to go either to the sea or to the mountains. There is no intersection. They are totally different areas, but you may like both of them. So they can be offered by IT system to you as a recommendation of your vacation venue. So this is the rule. Seaside, mountains, puddle problem, left and right, and so on. So we actually split it into such rules. And then immediately you have this problem, which actually starts or initiates by having two the same antecedents. So that's why just explaining how we got to the setting. We are interested what happens, because if we have antecedents that are different, at least up to this level, everything is easy and solved. It's finitary condition, Irina proved it, you have solvability. But then you don't have really two alternatives because they are disjoint. They are never like fired at the same time. You choose. So we were interested, what if we put them closer to each other? And we started from the extreme case, when we put them to the closest potential case when they overlap fully. And then it models this interesting example for us. So that's the story behind how we got to this problem. Just to learn how they behave. It was not like, let's do it artificially, but we were like thinking, we still don't understand Mamdani. People use it for functional dependency. We have much better rules for functional dependencies than Mamdani. Let's be frank. But maybe they give us a nice rule for alternatives, which are disjoint. But if we deal with them in the, say, old school way, we will be always unhappy because we will be crying like, oh, this is inconsistency. They didn't work. They work. They have no inconsistency in this case. They can be useful for alternatives more than for functional dependencies. That's the whole story behind. Leading to open problem.
Yes, please. Maybe the last question. There is a microphone. It's a microphone. I'll give you the time.
I was just wondering, you finished with Gödel algebra. Did you find, that equality always holds for any algebra, or is it restricted to Gödel algebra?
It was just example to draw it in Mathematica. This was in Gödel algebra. This one was, as you can see, in product algebra. We were just using residulated lattice properties, nothing else.
Yeah, but
and then in simulations, anything, or we were even trying to find counter examples based on different algebras, hoping that, for example, in product it will be easier because of the strict theorem.
Okay.
We didn't find even counter examples.
Then you made some simulations, and how did you perform your simulations? Did you, try out lots of algebras, or like whatever, a family of T norms, a family, or a parametrized family of T norms? Did you try that out?
No, just the predefined ones, like the standard ones.
Okay.
It was not like, it was not generating of 1,000 artificial problems. We're like trying to put there, our wisdom, but probably there was none.
Yes, thank you, Martin.
Thank you very much.
And we're moving forward with the next talk, fuzzy inference system based on the rule comparison measure. And Uriel Larea Asier is going to present this.
Okay. Thank you, Olga, for your introduction. So I will continue from some ideas from Martin because he explained the Mandami system, so we use it. It will make me a bit easier than my talk. Okay, this work has been done within Pamplona and Brazil. That Garzaliz is here, with Javier Fernandez that is coming a bit later, and Humberto that unfortunately couldn't come because he has a surgery next week, but it's okay. So, yeah, no, it's not a big deal, but some of you have asked. It's very disappointed to not have come. Okay. So, the goals of this work are to define a comparison measure between two fuzzy rules. And afterwards, with this comparison, be able to select the best conclusion from a rule system. So maybe I can help to solve or to the problem what side of the paddle have to the child choose. Okay, Martin explained how a rule is. For this system, we have a fuzzy set on the antecedents and consequence. And once the inference is done, we will construct a new rule with the input as the antecedent and the conclusion as the consequent. Okay, it will be important for the method to choose the outcome. These are different inference methods. There are no important. We can use the ones we want, and afterwards we will choose the best. Okay. So in Pamplona, we like a lot aggregation function that are some function from 0, 1 to 0, 1, bounded in 0 and 1, etc. You know all of them. And for this work, it's especially interesting recalling the Yakar index. That is a comparison between two fuzzy rules. Okay, I think you know in general for discrete fuzzy set that I not told before, we do the sum of the minimum divided by the sum of the maximum, and it's a measure to compare to a fuzzy set. But also we have another measures like overlap indices that especially give a value of 0 when there is no overlapping between the two fuzzy sets, and another value when there is some overlapping. It's important for this work that recalling that some overlap indices give a value less than 1, even if they are equal the two fuzzy sets, if the overlap index is not normal. And also we have similarity measures that also measure the similarity between two fuzzy sets, but in a different manner. Okay, in this case, we have a value of 1 when all the points of the fuzzy set are equal, but we have a value higher than 0, even if they do not overlap, because in this case, we have 1, 2, 3, and 4 points of the fuzzy sets that are equal. So with those functions in mind, I will explain what's the idea between before our comparison measure, and it's a comparison that should be symmetric. Also, we say, or we decided that when the antecedent or the consequence, I always choose the antecedent to not put two pictures, but if they do not overlap, the comparison will be 0, even if the consequence are more or less equal, because in a lot of fuzzy inference systems draw erroneous conclusions if the fuzzy sets are very different. And we say that the comparison should be 1 if all of the fuzzy set on the antecedents and the consequence are 1. More formally, is the same expression, symmetry. If they do not overlap, it will be 0, and if they are equal, it will be 1. So now we have different situations. In the first one, we will expect a comparison measure of 0 because those two do not overlap. In the second one, we would like to have a comparison value of 1. Here, it will be a comparison value between 0 and 1, and also here. In this one, we have to keep in mind that some overlap indices will return a value of 1, whereas a similarity measure will return a value less than 1. And here, the similarity measure will be 1, and some overlap indices could return a value different than 1. It's important for the second construction of our measure. So the first one is quite simple. We use a Yakar index and a function that is bounded. We have a value of 0 if either of the two values is 0. We say that if the consequence of the antecedent do not overlap, it should be 0, and it will be 1 if both are 1. So this will be the expression for comparing two fuzzy rules, in which we aggregate the comparison between the antecedent and the consequence. And the second expression that uses overlap indices and similarity measures is a bit more complex because first we compute the overlap index and similarity measure of each of pair of fuzzy sets. Then we aggregate to those results, and finally all of them in the. Yeah.
What is theorem? What position of the theorem? Because it starts let be the following.
Yeah.
Position.
Yeah. The idea is having those functions, we construct the following comparison measure. Is the second part, yeah. So the idea is that this expression is a comparison measure if we have an overlap index, a similarity measure, and those functions. Yeah. So as I said, we compare the antecedents via the overlap and similarity index, similarity measure, sorry, and then we aggregate like before. And in this case, we divide by the aggregation of overlaps to normalize and get the value of 1. So that's the main idea, but in general, rules do not have only one antecedent. So we have to generalize to multiple antecedent. And as I said, the idea is just the same, but in those cases, the function m has to be n-dimensional. So in this case, it will be 0 if any of the antecedent pairs do not overlap, or the consequence, and it will be 1 if all of the antecedent or consequence and consequence are 1. And the construction are the same, but multidimensional. It's just the same. I think it's not especially important. Also with the second construction. And now is the method to choose what is the best conclusion from a rule and a fact. The idea is quite simple. We have some different inference methods. We compute for each of them the conclusion. We construct this new rule form with the fact and the conclusion we have computed, and we compare that rule with each of the, or with the rule we have before. And finally, we will say the conclusion that it gives a higher comparison value. In the case of the child that had a paddle in front, if we do the aggregation and we choose the center, it will draw less comparison value because there is no rule that says if there is a paddle, you have to go straight. But if there is an inference method who chooses go right, that comparison should be higher because the conclusion will be if there is a paddle, then go right. No? I don't know if it's clear my idea. Okay, but also in this case we have only one rule. In general, we can have more than one. In this case, also, as Martin said, there are all rules. There are different methods to solve a rule system with a fact. And in this case, the decision-making process is quite similar. We compute for each method the conclusion for the new rule. And in this case, we have to compare this rule with each of the rules from the rule base. And finally, we aggregate all the comparisons to have only one measure for the method that we are studying. And I have a application just to show the idea. In this case, we have rules that, based on the age and the C-reacting protein value, determine the survival expectancy of gastric cancer patients. So there are these 11 rules, and we choose just to test our method for different cases, and 12 inference methods that are a parameterization of the compositional rule of inference and the Thales interpolation method. In this case, I have only chosen one of the construction methods because I think it's not especially relevant to show a lot of numbers. These are the methods, and just to show, in this case, we see that the method A, that is an interpolation method, gives the best result because the rule form by the conclusion and the fact that we are studying is more similar to one of the rules that is in the rule base. And that was my work. And what do we have to do from now on? We are studying also what do we have to do with continuous fuzzy set, because this study was for discrete, and also we have to see what happens when we are doing classification, and instead of a fuzzy set in the consequent, we have a class. And we want, but much later on, study also what happens with different rule systems like Takagi-Sugeno, etc. So thank you for your attention. If you have any questions.
Thank you. Thank you for your talk, questions, comments.
You know, so yeah, it's interesting approach, and I would like to make some few comments, yeah, on this approach. So no, you know, because this is just a quick reaction, yeah. Look, where is the difference between what Martin proposed, yeah, and what you are proposing, yeah? So in the case of Martin, say, or Mandana Sirano, whatever, yeah, so approach, yeah, the similarity, the measure, yeah, was extracted from the algebra, actually, yeah, you know, so yeah, the similarity was 1, actually, yeah, and this is 1 minus equivalence between sets, yeah, that's it. And therefore, yeah, having this, and this similarity is intrinsic, yeah, to the system, because everything is based on 1 algebra, right? And therefore the result is expected, so the consequence is expressed according to the measure and using facilities of the same algebra. In your approach, yeah, you are just jump up, yeah, so this means that, yeah, you just have one system and various algebras, yeah, say, yeah, and you are trying, yeah, to find, say, the best possible consequence, whatever, because, yeah, of this generalized modus ponens, right? Yeah, and therefore you imposed, yeah, measures that are above algebras, you know, so, and therefore, yeah, you are forced, you know, so the drawback of your approach is that you need to have all algebras, yeah, in order to produce all possible consequences. And after that, yeah, you can make your decision, yeah. Okay, it's possible, but it's, you know, so complex, it's complex, I mean, from the point of calculation, yeah, and it's time consuming, that's all, yeah. So the point is, the question is, yeah, in which framework, yeah, do you need to solve this optimization problem? So thank you.
To say it right, I don't know exactly how to answer that. Our idea was that sometimes we have different noise, like, you know, I think I have it at the start. Well, yeah. You know, you can use a method with different parameters, and yeah, it's not a problem. But often you don't know what to choose. We choosing a minimum or a product. So with this method, the idea was to make a decision-making system to choose the best. Maybe it's not so theoretically supported as the Martin's. I don't know.
Can I just give also my comment regarding the algebra? So if it's possible, could you show the previous slide with the algorithm? No, when we have like 1 minus the metric between 2 observation, not that one, but you remember you also said it's like a sum of 1 minus the metric between 2, but actually in this case, actually it was further on, when we have a sum of 1 minus the metric e minus.
In your example, that was
In your example, yes.
Okay. Yeah, it was the similarity measure. Yeah.
Yes, that one here. Yes, exactly. When you're speaking about the algebra. So actually, in this example, it's example when we use the Lukasevich algebra and the aggregation. So really, that one could be also used for other algebras. And yes, but then you need to, there should be not the sum, but the other aggregation, and yes, everything should be changed. But regarding the algebra, it's possible to use another algebras in that levels. and to see the results. But it's usually the question which algebra should we use and other. So the other questions. So thank you one more time. In this section, generalized Takachitogena Kang fuzzy interference system on intensity modulated radiotherapy treatment selection, and Gonzalez Garcia Xavier.
So, Jakuyem, Olga, and welcome everybody to this presentation. I am glad today to introduce you to our work, which is made by Lubka, that is there, Joan, that is my master thesis supervisor, and Umberto, that is my PhD supervisor. He couldn't come as I told before. So I'm going to start because there are a lot of things that I want to tell you now. So maybe you heard about Takagi Kang, but not radiation therapy. So let's start about defining what is radiation therapy. Okay, so basically, radiation therapy is a cancer treatment which consists on delivering radiation particles to damage the DNA of the tumor cells. And which is the problem here? Well, even the DNA is affected of the tumor cells, radiation particles also can damage healthy cells. So here we can see the problem of planning a radiation therapy treatment, which is known as dosimetry, as maximizing the radiation received by the tumor while minimizing the radiation received by the healthy tissues. Okay? So there are a lot of kinds of radiation therapy treatments. And in this work, we are focusing on intensity modulated radiation therapy, which is given by this kind of big hand. Is known as a linear accelerator. And this machine is the, can deliver radiation particles. So the idea behind the optimization of this kind of treatments is to optimize the angles from which the linear accelerator can fire the radiation particles, okay? And this planification is very expensive, sorry. And that's why radiation therapy is an static method, which means that even if you start, if the planification is made the first day, every single day, the same dosimetry is applied for each patient, okay? That's a static treatment. But nowadays, with the rise of artificial intelligence method, there is an area inside radiation therapy known as knowledge-based planning systems that aims to adjust the radiation when the patient is on this bed. No, so every single day the treatment is adjusted. This leads to adaptive radiation therapy. So there are mainly two problems with this kind of knowledge-based radiotherapy plan system. The first one is that the outputs of this kind of methodologies only gives you an optimal treatment, a single one. And the second one is that this outcome is not, is not giving you an explainability about why that treatment is the optimal one. No? So let's start talking about which are the metrics or the information to decide why a treatment is good or not. There are two kinds of information. The first one is the qualitative information. A clinical can see this kind of dosimetry and tell us, oh yes, this treatment is good because the tumor is here and the dosimetries, the doses are higher around the tumor, etc., etc. This is like the qualitative information. The second kind of information is the quantitative one. Well, there are several metrics and measures about the organs at risk and the tumors, and there are a bunch of regulation about this. Maybe the dose received by the percentile 99 of the heart has to be less than 5 yards. So this problem is a multi-objective optimization problem with a lot of constraints, okay? Which is the aim of this work? So we aim to develop an explainable artificial intelligence tool for a knowledge-based planning system in intensity modulated radiation therapy. Well, I'm not expert in this topic about explainable AI, And now I am considering to change this word of explainable for interpretable, as I learned a lot in the previous plenary. Okay, so yeah, basically the first thing we want to do is, well, the data is very important. We want to train a model in supervised manner for selecting the best treatment. No, we need data. We are using the knowledge-based planning challenge dataset, which provides us for several structures, segmented tumors, dosimetries, etc. But which is the problem here? In fact, for selecting the best treatment, we need several choices. And here we only have the original treatment. No? So our first contribution is a intelligent data augmentation technique. So our idea is to try to replicate treatments, synthetic treatments that might be similar to the original one, but with different branch of qualities. Okay, we want to generate treatment of different qualities. For this purpose, we are using diffusion probabilistic models, which are very commonly used now in generative AI, in our predictive task. But the idea behind these models is that starting from a random Gaussian isotropic sample, there is a denoising process characterized by conditioning information. Conditioning information in this case is the computed tomography of the patient, the organ segmented, etc., and you obtain a dosimetry. By this way, we are biasing this kind of models in order to obtain different qualities of treatments. So now, for a single patient, we have the original treatments, but synthetic and realistic treatments. No, as you can see here, if the original treatment is this one, here the contours are the organs, and the pixels, the color is the radiation. No, we have different models that generate a lot of outcomes. Here you have higher doses. Here, it might be that it appears a rotation, etc., etc. Okay, the first part is explained. We can discuss after if you want a bigger explanation, but here is the important thing. Now, the generalized Takagi-Sugeno-Kant fuzzy system. In the previous talks, they have been talking about Mandani. In this case, we plan to use Takagi-Sugeno-Kant. Why? Well, which is the difference? The difference is in the consequent. Here, the consequent of each rule is a real valued function. Why we use Takagi-Sugeno-Kant here? Because we want to predict the quality. And why we need that number? Because if we have several treatments, in order to establish an order among them, we need a quality number. No? Then for each treatment, a single value is predicted. We don't care about the value. Either it's 7, 100, or minus 500. We only want to establish an order. And why this system is explainable or interpretable? Because after establishing an order, you can take the best treatment and see which rules are activated and which premises make the activation or force the activation of that rule. So it is like a tool for the clinicals to see, okay, this treatment is good because this, or this. Okay, we are going to see an example after. Okay, so we don't use the baseline Tesseca model. We plan to generalize this model because we identify several weaknesses in some situations, not always. The first one is here, the use of a weighted sum. The use of a weighted sum here do not take care about the coalition between data. Think that here the information that is represented is the activation of the rule and the consequent. Okay. The second weakness is here. In fact, the consequent is represented by a linear function. Okay, real valued function. Why? Well, we can generalize more that for amplifying the space of solution. Well, the model is going to be more complex, but maybe in certain situations, you need that complexity. And the last one is in the AND operator here. That is represented with a T-norm, usually the minimum or the product. Okay, so premises are linked by an AND operator. As I have told, the weighted sums do not consider interaction of the data, unlike fuzzy integrals. the use of linear function restricts the problem. And in situation where when high uncertainty rules, maybe a rule is true, but there is external information that can condition the outcome of that rule. Maybe it's better to use an averaging approach instead of that AND operator, the T-norm, okay? So let's start replacing that AND operator. In fact, we propose a novel family of aggregation functions that we call submaxitive. So basically, submaxitive aggregation functions are bounded between the 0 and the maximum well, less than the maximum if the input data is not full of the same element. Okay, this second condition is needed in order to be an aggregation function. ¿Vale? This is an example of a submaxitive aggregation function which is not an overlap, a T-norm, or averaging. It's something else. But there are a lot of averagings, all T-norms, and overlaps that are also submaxitive. We are currently now working on characterizing this kind of subfamilies into submaxitive aggregation function. So basically, the generalized Takagi-Sugeno-Kan fuzzy inference system can see as this one. Its rule is connected by a submaxitive operator. We have to decide one. In fact, the AND operator is a single case. Then the linear function is replaced by any function. Here we can apply maybe a neural network instead of using a single a linear function. And after that, all the data is aggregated, the outcome, the final outcome is aggregated through a fuzzy integral. Here we need to decide which fuzzy measure are we using. Okay, so basically this is the idea of the generalized system. It is a generalization because a particular case is the baseline TSK. Okay, so the experimentation. Well, we are working in this right now, but the Public Hospital of Navarre provides us a rule system, a rule-based system of how can we measure if a treatment is good or not with 10 rules. See that here we have like a clue about this rule will be related with a bad treatment, with a good one. Here we can see that this is similar to Mandani, but as we have to establish an order, we need a number, okay? So yeah, basically the variables that we are using here is like the dose mean received by the esophagus, the 0.1 centimeter cubic maximum dose received by the spinal cord, etc., etc., etc. And we are using 3 fuzzy sets for each variable, low, medium, and high, that are fixed. We optimize this with an adaptive neurofuzzy classifier that is a neural network that replicates the TSK with our modification. And what we are seeing in this specific problem, this is not for all problem, is that the function we proposed before and the OWA, that if the orderness is less than 1 is also submaxitive aggregation functions, are having better results predicting the quality of each treatment than the product. Okay, so we have here some statistical test, and even if the well, it's not the centroid, it's here is the weighted sum. Sorry, it's even if it's not significantly better to use the Sugeno integral or a nonlinear consequent than the weighted sum and linear, here in the aggregation, there is significant. Okay, so how is the explainability of this system? Here we have 2 cases, a poor treatment. A higher score is that the similarity to the original treatment is high, no? And a decent treatment. Here we can see that the rule 8, 6, and 3 are the most activated one. In fact, the rule 8, the clinicals told us that the rule 8 is related with a good treatment. So this makes sense, no? The decent treatment has a more activated rule 8. And the poor treatment has a higher activation in the rule 3, which is linked with a bad treatment. Okay, so this is not all. Inside each rule, we can see which premises are forcing the activation of that rule. For example, in the rule 8, we can see that This is a head map that these premises are forcing that rule to be activated, because we are using here the submaxitive function, not a minimum, not a product. Okay, so basically this is the global framework. From a computed tomography and organ segmented, we can generate a lot of treatments, different treatments of different qualities, and then our generalized second model implemented with an adaptive neurofuzzy inference system give us the best treatment and why. Okay, so the contributions are a data augmentation model supported by probabilistic diffusion models, a generalization of Takagi-Sugeno fuzzy system, another family of aggregation function named submaxitive. We are now working in developing these all things, and an explainable knowledge-based planning framework for IMRT. Okay, future work. So we have tested this generalization only in this work. This doesn't mean that in every single case the submaxitive functions are better, etc. No. Then we have to study more those kind of functions, and finally, this work is possible thanks to a strong collaboration between clinicians, mathematicians, data scientists, a whole team, not separated. Okay, so thank you, Jakub, to all.
Thank you. Questions?
Only simple question. Why did you use in the antecedent of the rules disjunction and not conjunction?
Yeah, because
it is strange. Logically, it has little sense.
Okay, disjunction is not disjunction, because disjunction it will be the OR operator, no? But here, submaxitive functions are bounded between 0 and the maximum. Well, yes, no? O sea, the thing is that using an OR makes no sense in a rule, because if it is called and it rains, I'm going to take a jacket. If I'm going to take a jacket, even one or the other one is the same to split that rule into rules and avoiding that OR operator. So we think that it makes no sense to use disjunctive operators, so that here we only are taking into account t-norms and operators, but also averagings who, well, weight different premises. Okay, I don't know if that was the question or.
Some other questions? Yes, please take this microphone because.
I thank you for your talk. I didn't get how you evaluated the quality of your results and what kind of submaxitive aggregation functions you used in your experiments.
So basically, the quality is the outcome of the rule system. So, and a quality of 1, for example, a score of 1, it means that the dissimilarity from the original treatment, because we train this in a supervised manner, we have the original treatment, so we can measure how distant is our predicted synthetic plan to that one. Okay. And the submaxitive use function, it's been this one, well, this one is just an example, but I decided to use this one because it's nor a t-norm, nor an averaging, and nor an overlap. It's something that it is inside submaxitive aggregation function, but it's not inside a classical family of aggregations. No, it's the arithmetic mean. If the minimum is maximum to alpha, the alpha is a parameter between 0, 1, and or the product otherwise.
Okay, thanks. But why is how distant it is from the original treatment like a sign of quality?
The similarity, it can be, for example, the mean square error or whatever. We are using like the difference from the original treatment and the predicted one. There are 2 images, and you can compute a dissimilarity measure between them. What is the question?
Yes. So why is that good? You know, I mean, if you have an actual
Okay,
treatment,
yes.
why would that be good?
We are supposing that the original treatment, which have been given into
Yes.
a real case scenario, is like the perfect one. We are talking about radiation therapy and plannings that have been made in a real case scenario. So yeah, but we don't have more information, you know, well, an idea would be to say, okay, we are generating a lot of treatments, and there a clinician is in a supervised manner telling, yeah, this is to quality, this is 2.5, etc. But we don't have access to that. So we have to develop something to measure the quality of each synthetic treatment. And we decided to do it with that similar.
Yeah, it would be, I mean, it would be better maybe to like evaluate what's the effect of the treatment, if the treatment worked or not, you know, in the future. Well,
Yeah,
you know, the
but
physicians
here
might be wrong,
working
you
with
know.
radiation, maybe
Yes.
it's a little bit scary.
No, but maybe you have real data, you know, so maybe you can actually
I
somehow,
don't, in this,
you know.
well, it is very difficult to obtain this kind of data. So that's why we have decided to use the Open Knowledge Base Planning Challenge, because it provides a data set with certain information, and we develop all the work with this single information, even if the clinician help us with the rule base, like I said before. Thank you.
Thank you. Thank you.
Thank you. Do you have some more questions? Okay, then we close our section. Thank you once again for the last talk, and let's go to the lunch.